Welcome to lecture number 6 for ECE476 Advanced Embedded Systems. In this lecture, we're looking at binary inputs. So in this lecture, we'll look at how to read a single button. For example, this is button 15. When I press it, I get a 1 and a 0. We'll look at how to add more buttons. So here I've got 4 buttons. As I hit each button, I get a logic 0. My program can then use that to do various functions. We'll look at how to build a program that reads the level of an input. For example, here's a debate moderator. As I'm talking, my time runs down. When the time gets to 0, my microphone shuts off. We'll look at how to play a game of Hungry Hungry Hippo, where as the players hit their buttons, it keeps their score. So that's some of the things we'll be doing in this lecture. So starting out, with the Raspberry Pi Pico, each GPIO pin can be either inputs or outputs. It's similar to our last lecture, where logic level 0 is 0 volts and logic level 1 is 3.3 volts. For inputs, you got to be a little bit careful on the I/O pins. The Raspberry Pi Pico is rated to 3.6 volts, but 5 volts is way out of specs. So do not try to apply 5 volts to the I/O pins. If you do, no guarantee what happens. So again, this lecture is looking at using binary inputs. So we're going to read push buttons, keypads, convert voltages, resistances, temperatures to logic level 0 volts, 3.3 volts, count edges, build voting machines, count time for debate moderator, and multiple edges for Hungry Hungry Hippo. So starting out, if you want to read a single push button, like on your Pico board, there are 2 push buttons. I can read those as binary inputs. The trick is each of these buttons, when you press it, it ties the pin, the GP pin, to ground. So to read a button, there's actually kind of 3 different options. I can assign a pin to input. The first option assigns pin 15 to input, but it's floating. It's up to the hardware to drive it to 0 volts or 3.3 volts. Second option is I could have an internal pull-up resistor or an internal pull-down resistor. Now what that looks like is if you have it just as an input, it's floating. It could be 0 volts, could be 5 volts. The hardware is responsible for assigning the voltage. The second option, if I do a pull-up resistor, there's an internal 50K to 80K internal resistor tying it to 3.3 volts. In that case, if I do nothing, I'll read logic 1. If I ground it, I read logic 0. The third option is I could have an internal pull-down resistor. So both pull-up and pull-down can be used with a switch. If I use a pull-up resistor, then to read the switch, I'll tie the switch to ground. When I push the button, I'll read 0 volts. When the button's open, I'll read 5 volts, or 3.3 volts. If I use a pull-down resistor, then it's up to the hardware to pull it high. If I do nothing, I'll read logic 0. Tied to 3.3 volts, I'll read logic level 1. Now, generally, the former is what's used. That's a little bit safer. Again, you kind of notice in the lectures, occasionally I'm mistaking saying 5 volts. I should be saying 3.3 volts. Some processors use 5 volts, some use 3.3 volts. If you mix it up, you might harm Pi Pico. Ground is always ground, however. So it's safest to use the internal pull-up resistor, in which case you're going to get 3.3 volts when pulled high, and ground it. The second case is a little bit dangerous because if you screw up and think this is a 5-volt device, you might harm the Pi Pico. So for pretty much all these lectures, pretty much for this entire course, we'll be doing internal pull-up resistor, tying it to ground, and that's how your Pi Pico board's built. When you push the button, it grounds it. So, to read the push button being pushed, I'll use the following code. What this does is it sets up the button number 15 to be input, internal pull-up resistor. When I press the button, I read 0 volts. If I then display the button value as I run it, I'll see when the button's released, I read logic level 1, the pull-up resistor. When I press the button, I get logic level 0. So that's what's happening right now. So you can see the default is logic level 1. Oops, hold on. There we go. Default is logic level 1. When I hit the button, I get logic level 0, release, press, release. So I'm able to read logic levels. I read button pushes. Now occasionally one button isn't enough, so the Pico board gives you 2. Occasionally 2 buttons aren't enough. If you want more buttons, that's actually fairly easy to do. Just take whatever GPIO pin you want to use, tie it to ground through a push button, and then logic level 1 is no button push, logic level 0 is a button push. Just set up each pin as input with a pull-up resistor. So here's what's happening. I'll show you the hardware. I've got my 4 push buttons tied to ground. Each push button is then tied to GP 18, 19, 20, 21. As I push the buttons, I read logic level 0, second button, third button, fourth button. I can read the push buttons. And you can do that with all 25-ish I/O pins if you want. This is not real efficient, however. It uses up a lot of I/O pins. There are other ways to do it, but that'll be a future lecture. Kind of a sidelight. If I want to do a logic function like AND or NOT, I can do that in software. Anything you can do in hardware, you can do in software. For example, the switches I'm using are normally open. When I press the switch, it closes it, so that's actually a NOT function. When I push the button, I get 0. Button released is 1. You can buy switches which are normally closed. When I push the button, it opens. So a normally closed switch would give you the function X. A normally open switch gives you not X. That's a NOT function. If I place 2 switches in series, that's actually a NAND function. The output will be 0 if C and D are pushed. If I put the switches in parallel, I get a NOR function. The output is 0 if E or F is pushed. And back from digital system design, if you have NOT, NAND, and NOR, you can implement any function. So I could actually do functions all in hardware, just using switches, using normally closed, normally open switches, series, and parallel. And I can do about anything. That's in hardware. Just kind of a sidelight. You can also do it in software. Okay, so that is push buttons. Now, there's another way to get data to your Pico board. That's using a numeric keypad. Kind of looks like this. With a keypad, these are actually switches that are open and closed. So when I push the button 1, it shorts column 1 to row 4. When I push button 5, it shorts column 2 to row 3, row 2, and so on. So to read a keypad, there's a couple ways to do it. One approach is to connect the columns to 3 output pins. I'm going to use GeeekPi connect the rows to 4 input pins. I'm using pins 19, 20, 21, 22. Set these inputs to pull down. So if there's nothing connected, I read 0 volts. And then scan. In software, what I'll do is I'll output like a 1, 0, 0. When I do that, that's scanning the first column. If I hit any of the buttons on the first column, I'll read a 3.3 volt logic 1 on these pins. So if I see GP22 is high, I hit the 1 key. If 21 is high, I hit the 4 key. 20 is high, I hit the 7 key. 19 high, I hit the star. I'll interpret that as number 10. So I'm going to write 3 different subroutines. Or 2 of them. The first one is getKey. It's just going to sit there and scan the columns, scan the first column, second column, third column, see which button was pushed, return that value. The default is, if I don't have any buttons pushed, return to 55. So trying that, I'll write a little test code. I'll read the subroutine getKey and display what it is. So here on the keypad, you can see it over here, If I hit the 1 button, it shows up as a 1. No key pressed is 255. Here's the 2 button. 3, 4, 5, 6, 7, 8, 9. Star reads as 10. 0 and pound reads as 11. Okay, that works. The second function is readKey. What readKey does is it calls getKey. If the answer is 255, no key was pushed, wait until I hit a key. Save that value. Now read it again, wait until I release and get 255. When I release the key, return the value. So let's check out the function readKey. So right now nothing's happening. It's waiting for me to hit the key. If I hit 1, release, I hit a 1. 2, release, 3, release, 4, release, 5, 6. Okay, so readKey works. What that does is I'm going to get 1 keystroke every time I call readKey. Well, now that that works, let's put that all together. Let's set up a stack. If I hit the number 1, 2, 3, I'll read that as the number 123. And I do that, if the key value is less than 10, I'll just do times 10 plus value. So 1 becomes 10 plus 2, 12. 12 times 10 is 120 plus 3, 123. I'll interpret 10 as a push command. Push x to y, y to z, z to t. 11 is a divide by 10, basically clear out the number. Integer division. And print out the results. So if I try that, it's now waiting for key. Here's number 1, 2, 3. Star is a push. That pushes onto y. 4, 5, 6. Push. 7, 8, 9. Star is backtrack. 7, 7, 7. Push. This is a way to get numbers to your Pi Pico. Again, you could use the shell and use the keyboard, but sometimes you're not connected to a keyboard. If I want to have a standalone processor, I could use a keypad as a way to get data to it. Another way you can get data to your processor. The Pico is dumb. It doesn't know how you generate the voltage. It just reads 3.3 volts as logic level 1, 0 volts as logic level 0. If I want to read a binary signal, like is the voltage more than 2.3, what I can do is use a comparator. Use an MCP 602 op-amp. This is the rail-to-rail op-amp that operates single-sided supply down to 2.7 volts. Apply one side as 2.3 volts. If X is more than 2.3, the output slams high, logic level 1, 3.3 volts. If X is less than 2.3, it slams low to 0 volts. So here's the output, a nice clean binary signal. When X is more than 2.3, I get logic level 1. Less than 2.3, I get logic level 0. And kind of a sidelight, the op-amp you need to use is something like the 602. Don't try using a 741 or 833 op-amp. Those op-amps do not operate all the way down to 3.3 volts, and they are not rail-to-rail. What rail-to-rail means is that if my power supply is 3.3 volts, the output goes all the way to the rail, 3.3 volts. These two op-amps have about a 1 volt buffer. So if my power is 3.3 volts, I'll only get to about 2.3. I can't get to the lower rail 0 volts, I only get down to 1. And that's kind of a problem when you only have 3.3 volts to play with. If I lose 1 or 2 volts, that's a big deal. That's why I'm using the 602 op-amp. So I can read voltage. Suppose instead I want to find out, I've got some unknown resistance. Is it more than 2300 ohms? Well, one way to do that is change the problem to fit the solution. I know how to solve a problem if the output is a voltage. Convert resistance to voltage, and one way to do that is a voltage divider. If I choose the 2K resistor, then 2300 ohms corresponds to 1.765 volts. I want to switch at 1.765. If R is bigger than that, then X is bigger than 1.765. So I'll make the offset, the threshold, 1.765. What happens is if R is less than 2300 ohms, the voltage is less than 1.76 volts, and you get logic level 0 out. If R is bigger than 2300 ohms, it slams high, and you get 3.3 volts out. So this circuit gives you the logic is R bigger than 2300 ohms. I can do that with temperature. Take that resistor and replace it with a thermistor. For example, here's a thermistor that we use in lab fairly often. As temperature changes, resistance changes. Once it's resistance, previous solution. Use a voltage divider and a comparator. Now in this case, as temperature goes up, R goes down. As R goes down, voltage goes down. So this is what Vx looks like as temperature goes up. At 15 degrees Celsius, R is 1576 ohms. The voltage I want to switch at is 1.45 volts, so there's the offset. I'm going to connect to the minus input instead because I want, when it's really, really hot, meaning R is small, meaning voltage is small, I want the output to go high. So this inverse relationship, as the input goes down, the output goes up, means connect to the minus input. And again, you switch at 15 Celsius, which is 1576 ohms, which is 1.454 volts. All the circuit really cares about is voltage. So that's where I switch. So with binary inputs, I can now get input to my processor about voltage, resistance, or temperature. Or replace this with a light sensor, magnetic field sensor, whatever you want. I can get binary inputs relating to temperature, light, pressure, flow, humidity, your pick. Okay, so once I have a binary input, what do you do with it? There's actually kind of two types of programs. I can have level-sensitive programs and edge-sensitive programs. On a level-sensitive program, while the level is high, I'll do something. While it's low, I'll do something else. On an edge-sensitive program, I look at the edges, do something on the rising edge, and or do something on the falling edge. So to illustrate that, let's come up with a debate moderator. Now what the debate moderator is going to do is kind of monitor people talking. If one person's talking, speaking over someone else, it'll actually penalize them. So the idea is every candidate gets so much time, like 5 minutes to talk. Use that 5 minutes however you want. You can spend it talking over someone else. You can talk when it's your turn. However you want to talk is fine, but you only get 5 minutes. So what I want is a way to monitor when someone's speaking, decrement my time. When they're quiet, do nothing. When they reach 0, presumably I cut off their microphone. So there's the idea. This will involve both software and hardware. I'm actually going to flip it. I'm going to use the push button initially so that when I hit the button, the time starts decrementing. So to test it, I'm going to have my two buttons, my two inputs for speaker A, speaker B. That's the two push buttons, 15, 14, both pull up. Their initial time is 300 seconds, 5 minutes. And then in the program, if debater A is talking, I'll decrement their time. If debater B is talking, I'll decrement his time or her time. Print the time, wait 100 milliseconds, then repeat. So to test that, I can go to this program. Here's the two speaker times. Currently using the push buttons. If I hold down button A, A's time is decrementing. Release, stops. Hold down button B, B's time is decrementing. Hold them both down, meaning both people are talking over each other. Both times decrement. Okay, so that looks good. Now let's replace the push buttons with a microphone. So here I actually got a microphone from Amazon. This is a Dactoy high sensitivity microphone. As you speak, this is what the waveform looks like. While you're speaking, it outputs kind of pulses up to 3.3 volts, or plus minus 3.3 volts. When you're silent, it goes 0. I'll take that output, take it to an envelope detector. That's stage 2. What the envelope detector does is it pulls off the peaks with an RC time constant. If I'm quiet for a while, it goes down to 0. So the red line would be the output of the envelope detector. I then want to convert that to logic levels. When I'm speaking, I get 0 volts. When I'm silent, I get 3.3 volts. So here's my comparator. Compare it to 1.6 volts right in the middle. If it is more than 1.6, meaning I'm speaking, I'll get 0 volts out. Less than 1.6 volts, quiet, I'll get 3.3 volts out. So trying that over here in the hardware. Here's my microphone. Here's the envelope detector, one side of a 602 op amp. Here's my comparator. The output goes to pin 15. There, pin 15. Now in terms of software, as I'm speaking, it thinks I'm speaker number A. My time, speaker A's time starts decrementing. Take that same circuit, connected to pin 14, right there. Now it thinks I'm speaker B. As speaker B is talking, B's time is decrementing. So speaking, la 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 la, silent. Speaking, la 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 la, silent. You've got a debate moderator. That's an example of a level-sensitive program. As long as the level is 1, or in this case 0, it does something, decrements my time. While it is 3.3 volts, it does something else, doesn't decrement my time. Okay, that's a level-sensitive program. How about an edge-sensitive program? That'd be like a voting machine. I've got 3 people or 2 people running for election. As I hit a button, I want to record the button push. So I could take actions on the rising edge or falling edge, either one. If I pick the rising edges, rising edge on GP15, vote for A. Rising edge on GP14, vote for B. Now there's a couple ways of doing that. If I just have a single candidate running, what I can do is do 2 while loops. So what happens is I want to look for these rising edges. The first one is while the button is 1, I'm just going to sit there and wait. As soon as I press the button, I kick out. While the button is 0, I wait. As soon as I hit the button, I kick out. When I kick out, there's my rising edge. Add 1. Then repeat. I'm now back to the first loop. Wait until I hit the button, or release the button. Wait until I press the button. Another rising edge. Count. So that's one way to do it. The problem with this approach is it only works for a single counter. I'm locked up in this while loop, so I can't check the other buttons. Second way to do it is look for the 0-1 transition. I'm going to take the current reading, remember it, and the previous reading. So if the current reading is a 1, the previous reading was a 0, that's a rising edge. Ignore, 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 ignore. See another 1 and 0? That's another rising edge. So what that code looks like, this would be for 2 candidates. I'll make both pins input with a pull-up resistor. So A is the pin value, ZA is the previous value. Likewise for B, if the current value is a 1 and the previous value was a 0, that's the rising edge. Count. Likewise for B. So that's what I have here. I've got my 4 buttons. Actually going to use 4 buttons since I have that set up anyway. As I hit the button, I'll look for the rising edge. When I see it, actually hit the button press. This, because I'm using pull-up resistors, 0 is the current value. If the current value is a 0, previous one is a 1, that's a falling edge. Falling edge is when I hit the button. So press, release, press, release. There's candidate A, candidate B, C, D. I now have a voting machine. Finally, let's play the game of Hungry Hungry Hippo. So if you click on this link, this is actually kind of fun. This is 3 people playing against a husky. Who is the best at Hungry Hungry Hippo? Can you beat a husky? Well, the idea of the game is I'm going to have 4 people thrashing their buttons, sort of with a husky, and for 10 seconds, whoever hits the button the most for 10 seconds wins. So it's kind of similar to a voting machine, except the time limit is 10 seconds, and once the time is over, you stop counting. In terms of sampling rate, I'm going to sample every 10 milliseconds so I don't miss any counts. In this program, I'm going to use a thing called flags. A flag is something that tells the program or indicates that something happened in the program. Rather than display the count constantly, I only want to display the count when you hit a button. That's what the flags are for. If A hits a button, I'll set a flag. If B hits a button, I'll set a flag. If the flag is set, I'll print out the answer and then clear the flag. So this is a way that I can set up the program. Instead of constantly displaying the time and the score, I'll only display it when a button's pushed. That's what a flag does. It's not really necessary, but kind of cleans up the display, makes it prettier. In terms of how the program runs, it's similar to the previous program. I've got my flags. I'm actually looking for the falling edge because the way the buttons are set up, a button press is a falling edge, not a rising edge. So I'm looking for a 0-1 rather than 1-0 transition. If the flag is set, I'll display the current time and the current scores, sleep for 10 milliseconds, and increment time by 10 milliseconds. So when I run this puppy, there's the time. Here's the score. When you get to 10 seconds, 10 seconds, it quits counting, and player A won. And kind of illustrate what the flags do for you, if I get rid of that flag, this would be without the flag. It's constantly printing the time, which isn't necessarily bad. In my opinion, it's a little bit cleaner if you only print out the result on button pushes. So there's A in various buttons. I like to do a couple buttons at once, doesn't care. Now player C1. So that is some of the things you can do with binary inputs. Each I/O pin can be set up for binary input or binary output. For binary inputs, 0 volts is read as logic 0, 3.3 volts is read as logic 1. 5 volts is also read as logic 1, but you're not supposed to do that. Again, the manufacturer states that the maximum voltage that it was designed for is 3.6 volts. 5 is way above that, so if you apply 5 volts to your Pi Pico, no guarantee what's going to happen. You might kill it. With the binary inputs, you can control the program flow. I can look for levels, like logic 1, logic 0, and build things like a debate moderator. I can look for edges and build a counter for like Hungry Hungry Hippo. So that's some of the things you can do with binary inputs and binary or just binary inputs. And one thing to note, what we're doing is a little bit inefficient. I'm using up the I/O pins. That's not necessarily bad because you only you get so many I/O pins. If I don't use them, I don't get any money back. But I can use up the I/O pins pretty quickly. There are other ways to do I/O. I can do serial I/O. With only 3 I/O pins, I can control an unlimited number of devices. That'll be our next lecture. But anyway, that's lecture number 6 for ECE476.